We're going to do now a question on complex titration. We here have a potassium permanganate KMnO4 gradually added to a solution of iron salt, of ferrous salt. When they say ferrous, it means Fe2+. If they say ferric, it means Fe3+. The idea of gradually added means titration. Okay, so I have an oxidant or reductant, so an oxidation, reduction, reaction. The pH is maintained at 0. Now they said once the color of the permanganate remains and persists in solution, we get the equivalence point, and the reduction potential or the redox potential at the equivalence point is actually given to be 1.36. They ask us to calculate the E naught for the MnO4 manganese couple at pH 0, and another question after that. So they only give me the reduction potential for iron. So I'm not given the reduction potential for the permanganate. And I'm asked to get it. So remember, how did we used to get reduction potentials? Well, at the beginning, we got it from the hydrogen electrode and doing a galvanic cell. Later on, we were able to get it from the K expression. You get delta E naught, and then you can get an E naught for one of the couples. And now we're actually going to use the expression for the E at equivalence point of a one-to-one type to get the E naught. So this is not a one-to-one type, this is a more complex, and therefore I actually have to derivatize an expression for E at equivalence point. First, get a balanced equation. Now that is up to you. You have to react Fe2+ with the manganese oxide. Make sure you get a balanced equation. And I always recommend to do the 2 half reactions in the reduction form separately. Okay, so get the reduction form for the manganese, the reduction form for the iron, then get the E for both couples, add the 2 E's for both couples. You get an expression looking like this, okay? I'm not gonna do it, you try it. And remember, at equivalence point and in any titration, once there's an actual equilibrium that is achieved, the E at equilibrium, not necessarily at equivalence, but E at equilibrium for this couple, manganese couple, is equal to the E at equilibrium for the iron couple, which we call it E of the system or E at equivalence, whatever you like to call it, E of the solution. And thus we did an addition of both of those couples. Now at equivalence point and only at equivalence, do we have that the concentration of iron 2+ from the equation divided by 5 is equal to the concentration of the manganese divided by 1. It's actually the number of moles, but moles and concentration in electrochemistry can be taken interchangeably because they do not, the dilution does not affect the E. And therefore, I can get an expression where the concentration of Fe2+ is equal to 5 times the concentration of the MnO4. Likewise, Fe3+ produced is going to equal to 5 times the amount of the manganese produced. So we have 5 times more iron produced than manganese. Great. That being said, once you substitute into this expression the iron 2+ and the iron 3+ in terms of manganese species, you notice that all the reactants and products end up canceling in the log expression, and you end up getting an expression which only has H+ in the log term. And from here on, guys, I really do not want you to try to derivatize this each and every time. This is very simple to actually do offhand. E at equilibrium is going to be the same equilibrium expression as if it's a simple titration. So it's simply the number of electrons in one half reaction multiplied by the E naught of the couple for this reaction, plus the number of electron transferred for the other half reaction, multiplied by the E naught for this half reaction, divided by the total number of electrons, not of 5 times 1, like in delta E, in K expression, but 5 electrons plus 1 electron. So that was if it were a more simple, no H plus in solution. Now, because I have an H plus term in solution, I have to add a factor, which is plus 0.592 divided by 6 log of, now because I have a plus sign here, it means that it's, remember here, it's plus reactants divided by products. In this expression, so this is going to be plus log of, since the H plus is on the reactant side, it's going to be on the upper part of the log term. So it's going to be 8 H plus to the power 8. Now bring down the 8 and instead of log H plus put pH, you get minus pH instead of the H plus concentration. The 8 now has come down and you get this type of an expression. Clear? Now, of course, if you actually do it, it's also, the long way, putting everything down, not simplifying and memorizing how we do it, will take you a little bit longer. So do watch out. And when the pH is 0, this is nice enough, this whole term cancels and we're simply left with the expression for E at equivalence point, or E at equilibrium at equivalence point, for simple titrations. Okay. Now, once we have E naught of Fe, I could get E at equivalence point if I have the E naught of the manganese. Or, since I don't have E naught of the manganese, but I do have E at equivalence point, well, I can then get an expression for E naught of manganese. Substitute E at equivalence, substitute the E naught for Fe, and solve for E naught of the manganese, and you are done. So the E naught of manganese comes out to be 1.478. And now, this question has been modified slightly. We have been given a volume, but if we weren't given a volume, we solve it in one way. And if we were, we can solve it in another way. So if we're not given the volume of the ferrous salt, so we have a ferrous salt solution is decimolar. And when we say decimolar, it means that 1/10 of the solute in 1 liter of solution. So 1 divided by 10. Or 0.1 molar, 0.1 moles in 1 liter. And this decimolar amount of iron is titrated with the potassium permanganate at the same concentration. What will be the approximate concentration of the leftover or unreacted or MnO4 minus Fe2 minus species at equivalence? Well, to begin with, at equivalence, you would have thought that since the K for this reaction actually is quite high, you would think that there's absolutely the amount left of the manganese and the iron is pretty much 0, which we call epsilon, and 5 epsilon for the Fe2 plus. So how do we solve this if we don't have volumes? I have concentration, but I don't have volumes. Well, we know that at equivalence point, and you guys can show this, that 5 MnO4 equals the concentration of iron 2 plus, and that iron 3 plus is going to be 5 times the concentration of manganese 2 plus produced. Now, since we have the E at equivalence, that is just E at equivalence simply comes from E of one of the couples, remember? And if I have, the concentration of Fe2 plus, well, why not use E of at equivalence from the E of the Fe couple? So E of the Fe couple equals E naught of the Fe couple minus 0.592 divided by 1 log of the reductant divided by the oxidant, since I have a minus sign there. And therefore, what happens? Simply, now we have E at equivalence, and therefore, which is simply equal to the E of the Fe in my system, in my solution. Substitute for that, you have E naught of the Fe, get a ratio between the concentration of the two iron species. We also know the total initial concentration of Fe2 plus, and if the Fe2 plus reacts, remember from the conservation of elements, whatever Fe2 plus in solution I have plus the total Fe3 plus in solution that I have formed have to equal to the total concentration of Fe2 plus which I had initially, which is equal to 0.1. That gives me two equations and two unknowns, and therefore I can simply solve for both species. But what I do want is the Fe2 plus, so the Fe2 plus concentration is 1.08 times 10 to the minus 11. They also asked for the MnO4, and since the MnO4 is simply 1/5 of the Fe2 plus, and therefore solve for the MnO4, and that's going to be 2.16 times 10 to the minus 11. Well, that's one way of solving it. I find it a little bit of an easier way than this way, but here's another way of getting it. It's also not so difficult. It's good to know both methods just in case. Now here they actually gave me that I have 10 milliliters of iron. Even initially we didn't have this value, and we have the same concentration of the ferrous as the KMnO4. It's also a decimolar. So if I have my overall equation, I have a decimolar concentration of both the iron and the manganese, again at equilibrium, and at equivalence point we have we can relate the concentration of iron 2 plus to the manganese and iron 3 plus to the permanganate, and that's always at equilibrium as well. We have here C2V2 at equivalence equals C1V1 for the iron. And if this is equivalence, it means that if I do minus x, minus 5x, x, and x, that means at equivalence point, either both of these species will tend to 0, right? And so I could solve for x for both, and we end up getting C1V1 equals 5 C2V2, which of course is the same expression that we would get at equivalence point, since the number of moles of iron 2 plus is 5 times the number of moles of reacted Mn4 plus. And therefore, if you solve for this, you get C1V1 equals 5 times C2V2 at equivalence. We could also solve for the volumes at equivalence point from this expression. And just so you know, guys, all the time, if I want to get this expression quickly, that's it. C1V1 divided by 5 equals C2V2 divided by 1 for the stoichiometry, and solve for whatever you need to solve for. V at equivalence, okay, equals, I have the concentration C1 now, I have the volume C1, which was 10 mils, that was missing previously, divided by, I have also the concentration of the permanganate, now, and that I can find V2. V2 at equivalence is simply 2 milliliters. And so actually now I have a total volume. And if I have total volume, what I can do is get the concentration of the products at least, and look at the concentration of the products. That's simply X and 5X, which happens to be C2V2 and 5 times C2V2. Since now I have the V2 at equivalence, I can solve for the product's concentration in terms numerically. So this is C1V1 divided by total volume, which is V1 plus V2 at equivalence, equals and or 5 times C2V2 divided by total volume. Do the substitution, you get that iron 3 plus is going to be equal to 0.083 molar as a concentration, and multiply that by 5, you get the concentration of the MnO4. Sorry, divide that by 5, you get the concentration of the permanganate, of the manganate, Mn2 plus. All right, of course, I have these product concentration. It's minus epsilon on both sides, but the minus on the product side is negligible. And so on the reactant side, I only have, instead of 0, I should put 5 epsilon and epsilon for the manganese. And thus, if I have this expression, I could easily get epsilon from where? I can get epsilon from the K. Solve for K. The K expression, you all know how to get K now. You have the delta E naught, you have the 5, the total number of electron transferred is actually 5. Again, this is N times N, or total number of electron transferred. Do not be confused by any other number. It's not N plus N. This is N times N, or total electron transferred for both couples. All right, so we've done this enough times so you can get the K. Once I have K at equilibrium, I have K expression at equilibrium is products divided by reactants concentration at equilibrium. And at equilibrium, we have already the concentration of the two products. Don't forget to put the stoichiometry 5 here. So Fe3 plus to the power 5 divided by, here we have the MnO4, that's epsilon. The Fe2 plus is 5 epsilon, but also you have to put it to the power 5. And they gave us that the pH of the system is actually 0, so the H plus is 1. Notice I could actually modify this to at any pH value, so you could have modified it to any pH value. Solve for epsilon, you can get that epsilon, and that gives you the concentration of the both permanganate, and 5 times epsilon gives you the concentration of iron. Notice we have the same answers as we had in the previous type of question, and therefore, I don't know how, but I do somehow find it easier to do it this way. So anyhow, and this had less information given, but I do find it a bit easier.